Okay, let's now understand a bit more about the function e power minus delta E by kt. So when I have taken two different scenarios, I created temperature values from 1000 to 40 or 20 or something like that, very low value. Yeah, 40, 20. Now, here I made the energy difference of the same order as the initial temperatures. Okay. Um, so actually, I don't think we discussed that. So let me actually tell you the process of simulated annealing. So you start with a temperature parameter. We'll discuss about how we started with that temperature. After this section, it becomes very clear how you start with the temperature. And now what you do is at that temperature, you generate a random solution and you generate its neighbor. And if the neighbor is better, okay, depending on maxima or minima, you change the structure of the function as discussed in the previous video. But if the neighbor makes the energy or objective better, okay, you accept it always. If it makes it worse, you accept it with a probability. Now you try out a few alternatives at that temperature. Okay, so you got one of them finally as either it made it better or worse. Then you reduce the temperature a bit and you repeat the same thing again. And you reduce the temperature. You repeat the same thing and you reduce the temperature. So constantly you reduce. Now we'll see how this function changes as we reduce the temperature. Okay, here I have taken two cases. In case one, I'm reducing the temperature, but my energy difference is of the order of my initial temperature. Okay, I put it 1000, 1200, 1400, 1600. Now, at if my energy difference, my objective difference is of the same order as initial temperature, my initial acceptance is probability. A bad solution I will accept with a probability of 0.36 or 0.36, you see, or um, 0.30 if it's 1200, 30%, or 25%, or 20%. And then, so which means the worser the objective, the probability of acceptance is getting lower. Okay, when it is difference is only 1000, I'm accepting with 36%. When it is 1600, I'm accepting with only 20%, a bad solution. So if my objective is getting very bad, I will accept it with a less probability. That's a good property of the function. Then as I reduce the temperature, again, the probability that I accept the solution is coming down. At very low temperatures, the probability is so low that I don't accept bad solutions most of the times. I reject them, right? So the function that we created has these beautiful properties. If the solution is much worse than the neighbor, the original solution, it will accept it with a less probability. If the temperature is very low, it will accept with a very low probability. Okay. Now I plotted in this curve, mm, I made the temperatures, small difference I brought in, where my energy difference is to the tune of the end temperature. So initially, there's a huge difference between the temperature and my energy difference. Okay. So my temperatures are 1980 like that initially. I started with a difference in the objective function of 10, 30, 50, 70. The shape of the curve, as you can see, is very different from the previous one, though certain behaviors are maintained. So when at high temperature, when the difference is lower, one thing that you see is the acceptance probability, unlike in the previous case where it was 0.36, is very, very high, 0.99. So almost every bad solution is accepted, 99% chance that it will get accepted. And as the solution gets worse, the objective is much worse, it comes down like before. 99 has become 93, but still the acceptance is pretty high. Like before, as I cool it down, the probability comes down, but a lot more slowly, a lot more slowly, and then it drops. Okay, at very low temperature, it doesn't accept. Now, so depending on how I set my parameter, this behavior changes. Most of the time, I want you to understand this. Most of the times, it is better to start with something like this, where my initial probability is around 93 or 95%. So most of the times, the energy difference, objective difference, and the initial temperature ratio should be like say this 7%, 5%, like that, 1050. So that my acceptance of a bad solution is pretty high. And it stays like that for some cooling. And then I start accepting with less and less probability. Also, people do two types of cooling. The cooling that we looked at is geometric cooling. Okay, where if you go to the Excel, the formula that I used here, oh, this is actually linear cooling. Okay, the temperature. I have used 980, 960, 940. This is linear cooling. Okay, I could use a geometric cooling also. In fact, I encourage you to, let's actually do here itself. It will become a bit difficult for me to type all that stuff, but I encourage you to try out how that function varies with geometric cooling. What is geometric cooling? New temp is equal to some factor, let's say 0.95 times old temp. So 1000 becomes 950, 950 becomes 950 times 0.95. It behaves like this. High temperature to low temperature, it drops quickly initially and then tapers off. What I showed in the Excel is a linear cooling. 1000 new temp is equal to old temp minus some temperature, minus some 20 I used, or 10 or 1, whatever, it doesn't matter. This is linear cooling. So it doesn't matter which cooling you use. Normally, though I showed in Excel that linear, I normally go for geometric cooling, but there's no right or wrong answer there. So I want you to understand this function behavior, how you cool it, and depending on relative values of the delta E, that how bad the solution is, and the start temperature, there are some differences in the behavior of the function accepting bad solutions. I want you to clearly understand that. Okay, great.